Harmonic resonance is a topic that pops up in many fields, applicable to sound, such as in this example of two tuning forks, civil engineering, a famous example being the Tacoma Narrows Bridge collapse, astronomy, and the resonance of the orbits of Jupiter's first 3 moons, and of course, electrical engineering, such as using a Tesla coil to create lightning in your garage. In electronics, the common explanation of resonance uses either a series or a parallel RLC circuit. These basic examples are good for explaining the basic concepts, such as resonant frequency, but the derivation of these concepts becomes much more complicated when multiple circuit elements are included, which is a useful thing to understand if your circuit of interest is, for example, a power line that uses many capacitors to boost voltage along the circuit. What would the resonant frequency or frequencies of this circuit be? In a previous video, link in the description, I showed how to represent these more complicated ladder networks as continued fractions and briefly reviewed their harmonic resonances, where the impedance Z goes to either 0 or infinity, otherwise known as zeros and poles. This video is a part 2 to that previous video. In this video, I'll review certain patterns that appear in the harmonic resonances, then talk about how these patterns change when some variation occurs in the ladder network. Finally, I'll add resistance to the model, and we'll see how this creates damping of the harmonic modes. I hope to provide 2 lessons in this video at the same time. From a mathematical perspective, this video is a lesson about how to understand continued fractions built out of complex numbers. From an engineering perspective, this video is a lesson on the impact of harmonic frequencies on a ladder circuit. I'll briefly run through what I covered in the last video. Here, a ladder network consists of inductive and capacitive elements, noted by the letters L and C. If you're not familiar with inductors and capacitors, you can just consider the variables L and C as free parameters. All inductive elements are the same and all capacitive elements are the same. The frequency omega is the independent variable that I'm going to focus on the most throughout the video. Total impedance is labeled as Z, and in step 1, Z is expressed as a continued fraction. In step 2, a factor of root L over C is pulled out of the fraction, which very nicely simplifies the fraction by making every term in the fraction the same. Step 3 is just a variable substitution to simplify the fraction a little bit. I'll use this substitution for the letter U throughout the remainder of this video. In the final step, the imaginary unit I can be pulled out of the fraction, which leaves negative signs on every other term within the fraction. Here is the U substitution again, just as a reminder. Any continued fraction can be collapsed into a fraction of polynomials. The highest degree of polynomial that appears is the same as the number of levels in the fraction. For example, here the circuit has 4 components, the fraction has 4 levels, and the highest degree polynomial is the 4th power. Every time an inductor and capacitor branch is added to a ladder network, the continued fraction gains 2 more levels, and the highest powers of U in the polynomials goes up by 2. The values of U where these polynomials equal 0 will provide a clue about the dynamics of the total impedance when resistance is added to the network, which I'll review in a little bit. These polynomial fractions are hiding an interesting geometric pattern that's revealed when we look closely at their poles. Starting with the fraction for a 2-element circuit, the pole is equal to 0. This is also equal to 2 times the cosine of pi over 2, which I'm illustrating on the right using the green line on the semicircle with radius 2. The factor of 2 on the cosine may seem unnecessary, but it's part of a pattern that will seem more clear in the next example. Next, the expression for the 3-element circuit. Note that the denominator term is the same as the numerator in the previous example. This denominator produces poles of plus or minus 1, which on the diagram on the right corresponds to 2 times the cosine of pi over 3 and 2 times the cosine of 2 pi over 3, respectively. Next, the 4-element fraction. Again, the denominator is the same as the numerator in the previous example, and this pattern of repeated polynomials will continue for every successive element added to the ladder network. The poles are 0 and plus and minus root 2, which on the diagram on the right corresponds to 2 cosine of pi over 4, 2 cosine of 2 pi over 4, and 2 cosine of 3 pi over 4. I'll run through just a couple more examples of these polynomials to reinforce the pattern that's occurring. There's no obvious reason why the cosines of regularly spaced angles should be appearing here, and the proof for this is related to Chebyshev polynomials, which are a whole other topic which I won't have time for in this video. I've added a short proof explaining the connection to Chebyshev polynomials in the description for those that are interested. By the way, all of these examples do have a pole at infinity, but that doesn't add anything to the explanation. The pole at infinity will be illustrated in an example soon, but it's not an important fact to focus on. I'll summarize what I've reviewed so far. A ladder network with n repeating elements where each series element is the same and each parallel element is the same can be represented as a continued fraction with n levels, which collapses to a fraction of polynomials of order n in the numerator and order n-1 in the denominator. The poles and zeros of this fraction can be found by computing 2 times the cosine of regularly spaced angles, which are rational multiples of pi. Since these roots and poles are cosine functions, they are always real numbers, which means that if u is somehow a complex number, then the impedance z can never reach a pole or zero. This fact will become important in a few minutes when we add resistance to the circuit. Also, really quick, here's a slight variation of the rules you just saw, but for a ladder network with the first inductor removed. So this sequence starts with a capacitor. This changes some of the ordering of the terms and the indexing, which I marked in red font, but the overall rules stay the same. So all of the examples so far have had the same value for each inductor and capacitor, but now I want to show what happens when some variation is added. Here's a ladder circuit with 10 elements. Again, all inductor elements are the same and all capacitor elements are the same. The impedance chart shoots up to infinity at infinite frequency, but that's a minor detail here. There is a 9th order polynomial in the denominator, so there are 9 poles other than infinity, which all happen to be either the golden ratio or some related number. These poles carry on the same geometric pattern of being values of the cosine of regularly spaced angles, here multiples of pi over 10 from there being 10 elements in the circuit. Now I'll increase the size of one of the inductor elements up to a factor of 100. Watch how the location of the poles shift as the inductor increases its value. There are still some interesting patterns to pick apart here even after this shift. Here I'm highlighting in purple the circuit on the left side of the 100 element. This purple section looks like a 6-element ladder circuit from the previous examples. And here is the impedance formula for the 6-element ladder circuit. The poles for this circuit happen to be approximately equal to plus and minus root 3, plus and minus 1, and 0, which are poles that already appeared. So 5 of the poles for this uneven 10-element circuit happen to look like the poles for the 6-element circuit with self-similar ladder branches. Now I'll highlight the portion of the circuit to the right of the 100 in yellow. And here is the corresponding impedance for that 3-element circuit. The remaining 3 poles, corresponding to plus and minus 1.41 and 0.09, happen to be approximately equal to the poles for that 3-element circuit all by itself. So despite having inserted some variation where not all circuit elements are the same, there is still the appearance of this geometric sequence of angles that determine the location of the poles. Now, I'll go back to the ladder circuit with like series and like parallel elements, but this time I'll add resistance next to the inductors. I'll use specific values of inductance L and capacitance C that are similar to actual values one would find on a power distribution circuit. Also note that the chart here is not using the U substitution in the bottom axis, but the raw frequency value. When resistance is added to the model, the infinite poles and zeros are no longer infinite and zero. However, our geometric pattern is still there. Going back to the U substitution, when this is computed for the first decreased pole, the value of the golden ratio still appears. Resistance reduces the frequencies where the resonance occurs, but the resonant frequencies still approximately follow the same geometric pattern shown before. So why is resistance able to reduce the peaks? Let's take a closer look at the continued fraction for this circuit to find out. Here's the impedance equation for a ladder network with resistances next to the inductive elements. To start simplifying this, we need to redefine the elements with new variables. ZL is an impedance term which includes the effects of resistors and inductors, and YC is a conductance term which includes the effect of capacitors. In step 3, pull a square root of ZL over YC out of the continued fraction, which leaves the same term in every level of the fraction. For step 4, redefine the continued fraction terms using the substitution for the letter V times the imaginary unit. This is similar to the U substitution from earlier. For step 5, pull that imaginary unit out of the fraction, which creates alternating minus signs within the fraction. This continued fraction in step 5 will now collapse to the types of polynomial fractions associated with the geometric sequences from earlier. I said in the beginning of this video that I would be describing continued fractions with complex number entries, and that's where we've reached. ZL and YC can be represented as complex exponentials, with angles associated with the inductive and capacitive impedances, which I'll give more detail on in a second. V can now be defined as a complex exponential with an extra minus pi over 2 term that appears because of the imaginary unit that I forced in at step 4. With no resistance, the inductive and capacitive impedance angles are pi over 2 and negative pi over 2, respectively, and the reasoning for this is related to the behavior of voltages and currents inside those elements. These angles reduce the complex exponential in V so that V is just proportional to the magnitudes of ZL and YC, which is always a real number. However, with resistance, the inductive impedance angle is no longer pi over 2. So the complex exponential in V stays complex, and V cannot just be a real number. If V is not a real number, then it cannot just equal 2 times the cosine of any angle. So the poles and zeros of the impedance will never be reached. This is a purely mathematical explanation for the reason why resistance reduces the magnitude of harmonic resonances. The physical explanation is that resistance helps dissipate the resonating energy in the circuit. In reality, circuits that are not superconductors always have some resistance, so infinite poles are not a reality in most cases. To summarize my first continued fraction video and this video, I've reviewed how to describe a ladder network as a continued fraction and in a generalized way where the impedance and conductance terms in the fraction can be complex numbers. I showed how the poles and zeros of these fractions correspond to cosine terms of regularly spaced angles, which help provide context for why resistance creates non-infinite poles. I've found that continued fractions give me insight for understanding circuits in my day-to-day work, and if you're an electrical engineer, I hope you can find continued fractions useful as well. If you enjoyed this video, please like and subscribe below. Thanks for watching.